So I was asked by a few people watching my videos to make a video on the PZX triangle. It's also called the rational horizon diagram. So I thought I'll make one for you guys. Many students often get confused with whatever goes on in this rational horizon diagram because there is a lot to take sometimes. But I understood it very simply, and that's how I'll convey it to you guys as well. I hope you will find the explanation very simple. Alright, so I'll show you what is traditionally how it is explained, and I'll show you how I understood it when I was a cadet. Alright, so to understand how a rational horizon diagram works, you first have to understand how the earth, positioning on the earth, we understand the positioning on the earth. Alright, so the first diagram here, the first drawing here refers to the earth. So let's assume this is the earth. Alright, and you are here. This is Z. You are Z here because very soon when I will project you onto the celestial sphere, this will be known as Zenith. And Z stands for Zenith. That's basically the observer, that's you on the ship, when your position is projected onto the celestial sphere. Alright, then of course you have the North Pole here, you have the South Pole here, you have the West and the East here as well. Alright, and the WQE, this becomes the equator. Alright, so WQE is the equator here, right? And then of course this here is your latitude. So that's how it works on the earth, isn't it? But now what we intend to do is I want to take you as the observer from the earth and then project you onto the celestial sphere. Now when I draw a celestial sphere, which I have drawn a very ugly one, I should have drawn a better one. So when I project you onto the celestial sphere, this is the celestial sphere. Alright, so for the celestial system of position fixing to work, that is when you fix your position based on the bearing and angular distance from the celestial bodies, you have to be also assume that you are also in the celestial sphere. So when I project you onto the celestial sphere, I will project you and I will project the pole also to the celestial sphere, whether it's the North Pole or whether it's the South Pole. So when you come onto the celestial sphere here, your position is known as the observer's zenith, and that's why the Z. Alright, and now we'll understand everything from that point of view. So now you have to visualize that you are in the celestial sphere. This is a sphere of infinite radius. There is no radius here. Alright, now what do I mean by this is that when you consider the earth, this distance here is 90 degrees, right? Or this distance here is 90 degrees as well. Alright, but that's not the case with the celestial. The celestial sphere has infinite radius. It is of infinite radius. You cannot measure the celestial sphere, right? Because it's all over you. What, however, you can understand is, and I'll tell you that later, is that when we look at the celestial sphere and I place you in the center of the celestial sphere in such a way that I imagine looking at you as the observer from the top of the celestial sphere. And in that case, each point on the celestial sphere becomes 90 degrees of angular distance from you. I'll explain all that later, alright? So don't worry about that now. So for now, just imagine your celestial sphere, and this is of infinite radius. You can't measure it in any way, alright? So that's why the concept of distances will not work anymore. Only the concepts of angular distances, bearings will start to work, alright? Because with the earth, of course, every degree is 60 minutes or 60 miles. And that's why 90 degrees can be measured in terms of distances by multiplying by 60, and that's how it all works on the Earth sphere. But when we talk about rational horizon, we talk about projecting you as the observer onto the celestial sphere of infinite radius. Now if I talk about it in a different way, now imagine looking at diagram 1, alright? Now if I tilt the diagram 1 towards you, alright, as you are looking at it towards you, if I tilt the diagram 1 towards you, you will see that the pole moves downwards, right? The north and the south and the west and the east remain where they are because they are directions, right? And then the latitude circle that you are on, Z, also becomes a curved line. The equator that you see also becomes a curved line if I tilt the diagram towards you. Alright, so if the globe is tilted towards you, the point of P, Z and Q would move downwards, and both the equator and the parallel latitude would appear as curves to you, right? And the south geographic pole, of course, it disappears, because remember that we are tilting it towards you, so the south has disappeared now from your vision, right? Because you have to bear in mind that P, Z and Q are on the surface of the globe and not on a flat surface. Now if the globe is gradually tilted more and more until Z is in transit with the center of the globe would appear as shown in figure 3, right? Now since all the points P, Z and Q have apparently moved only because of the tilting of the globe, each has shifted out of its original position by the same amount. Therefore, NP here becomes equal to ZQ. Alright, but ZQ is equal to the latitude, right? Because it's been measured from the equator. So therefore, NP will be equal to ZQ will be equal to latitude. And then slowly this becomes the basis of the rational horizon diagram. So what happens here is that WQE here becomes the celestial equator, but it is not known as the celestial equator, it is known as equinoctial. Alright, but it is equivalent to the celestial equator, or rather equivalent to the equator on the Earth's surface, but in the celestial sphere. So the latitudes, or the observer's latitude, is measured in the reference to the celestial equator. Alright, and then of course P becomes the celestial pole. So this becomes the celestial pole. So this is the pole on the Earth's surface kind of projected onto the celestial sphere. Right, this north, south, west, east are directions only, they are for direction keeping purposes only. Right, so now we figured out ourselves. So now imagine looking at the celestial sphere from the top, so you can see the observer's head. That's the vision I'm giving you here, right? Now if we consider the movement of the celestial body, so the blue line here shows the movement of the celestial body in the celestial sphere. Now remember, you are all now in the celestial sphere. So celestial body means sun, moon, stars, planets, it could be anything. Alright, now of course, because the sun, or let's take the example of a sun, alright, here in the celestial sphere. Now the sun always rises from the east, so sun will start rising from the east here. Alright, this is the rising sun. Over here it reaches its meridian passage. When its meridian coincides with the observer's meridian, and somewhere over here, let's mark it as XS, and the celestial body is denoted by X. Alright, here, so this here is the rising body, and here is the setting body. Alright, so this is the journey of the celestial body in the celestial sphere, right from the point it rises in the east and sets in the west. Alright, so if at any point during the journey of the celestial body I join Z with X, that becomes the angular distance. That becomes the angular distance from you as the observer to the celestial body. Now you cannot talk about distances here, you can only talk about angular distances, that is measured in angles. Alright, because the distances are light years away, so you cannot talk about distances in miles or minutes or anything like that. Alright, so if I have to keep going, let me erase some of the things for you so that it doesn't get too cluttered, and I'll write down the new things now, because I'm sure you can go back to the video and watch it again on what the different things I've written, because I want to mark some more things here. So I'm taking all this off. Alright, now what else I can mark here is this angle here, your bearing from the body. So this becomes the bearing from observer, that is you, to the celestial body, and this is also called azimuth. And if you have been watching my previous calculation videos, you will know that I've always talked about bearing and azimuth in the same way, because that's basically the observer's bearing from the celestial body, right? Then this distance here, which is zx, right? I'll take out the r because the r was rising in the east. So this zx is now, what is it? Zenith distance. All right, this is the angular distance from of the celestial body from you. And again, if you have been watching my previous videos, the calculation videos, you know that I refer it to zx or zenith distance. So some books say call it zd, and we have the tzx, which is the true zenith distance, and we have mzx, which is the meridional zenith distance. That means the zenith distance when the celestial body is on the observer's meridian, that is at position x dash. All right, what else can we label here? We can label this this angle here. So when you measure the angular bearing from your meridian, from the observer's meridian, going westward to the meridian of the, or the celestial meridian of the body, that is called the LHA. So LHA always measured westwards from observer's meridian to the meridian of the celestial body. All right, so this is the LHA. Many books, and I'll change the pen here for you, many books they call this angle as the EHA or the easterly R angle. All right, but we don't use it much here or in our calculations, so but still I'm just letting you know because different books have different phrases. Alright, so that's how simple it is. It's actually pretty simple. I actually understood it. When I understood it, I used to just make one line first. So I used to assume, I used to take the case of the meridian passage. When this became my equator, Q used to become my equator or equinoctial. Then I would put myself or the observer based on my latitude, of course, given to me. And then I would put the celestial body based on its declination, of course. I'll put it somewhere here, or it could go down somewhere here, it could go somewhere down here. You don't know where it was based on the declination. And I started off understanding that how does all this works and where is the body bearing from you. And then slowly I understood that if the body is rising and setting from east to west, it would be pretty much the same concept. It won't get more complicated than that, right? So when we talk about the declination of the, so the declination of celestial body, declination of celestial body is like the latitude of the celestial body. So if the celestial body was on the surface of the earth, then we would be calling it latitude. Alright, so we have the concepts of latitude and longitude on the surface of the earth, but in the celestial sphere we have the concept of declination, which is equal to latitude, and hour angles, which is equivalent to the longitude. So we don't have latitude, longitude, we have declination and hour angle. Alright, now what is declination? Declination is very similar to, like I said, it's very similar to the latitude. So if you think about it, this here, this is the declination of the celestial body. So in this case you can see the declination is south, and what is the latitude? This here is the latitude. So this here becomes the latitude, and since you are north of the equinoctial, your latitude is north. In this case here, latitude is north and declination of the celestial body is south. All right, by what you can see, the latitude is greater than the declination by how I have drawn it. All right, so Qx will always denote the declination of the celestial body, Zq will always denote the latitude of the observer, then the angle PZX is the azimuth, and the P is the celestial pole, or the pole elevated from or projected from the celestial earth sphere to the celestial sphere. The Z is you, the observer, and you are looking at yourself from the top, and that's the view. The X, the declination circle, pretty much marks the journey of the celestial body. So if I go into the next diagram here, you can see what is the declination here. The declination is north here, right? Because you are north of the the celestial body is north of the equinoctial circle. All right, and what is your latitude? Your latitude is south because you are now south of the equinoctial circle. Now remember, whenever you are in the south, when the observer is in south, the view observer in south hemisphere or in south latitude rather, the view of the rational horizon diagram then takes the south pole view. So this you can see here, this is now the south pole, south celestial pole. So the whole view changes from the southern hemisphere's point of view. So the pole is not drawn in the north side, it is drawn toward the south side because that's the reference point. Alright, and that is why you move the equinoctial circle and you don't move you as the observer. So the observer stays in the center of the globe drawn. So basically you always look at the observer from the top. Observer should always be in the center of the globe, and you move the equinoctial circle around and the pole around. So if it's south latitude, the south pole is drawn, the north pole disappears from the view, and the equinoctial circle is shifted accordingly, and you go south of the equinoctial or north of the equinoctial by shifting the equinoctial circle. Alright, so over here you can see this is the latitude and this is the declination. And again here, by how I have drawn it, the latitude looks higher than the declination. The latitude's value is higher than the declination. Alright, again in the 7th figure here, you can see this is in the southern hemisphere, south latitude, your south, the declination is south as well, right? Because both the celestial body and you as the observer are south of the equinoctial. Alright, body is always rising. This is the rising body. It rises in the east and is always setting in the west. Right, this is always the meridian passage. Alright, the px, one thing I have not told you is px. Px stands for polar distance. Alright, and there is one last thing I want to tell you, not last thing, but one of the other things I want to tell you is, remember before when I started talking to you, I was telling you that on the Earth's surface, the poles are all 90 degrees from you if you are on the equator, right? So if you are exactly on the equator, the South Pole and the North Pole is 90 degrees from you. But that concept doesn't work in the celestial sphere. In the celestial sphere, and for that again I will erase some of the points here so that you can see, I can mark it for you guys here. You can always go back in the video and understand the rest of it, right? So I want to make it very clean so that I can mark things for you guys. So remember, in the celestial sphere, when you are zenith, when you are in the center of the globe and you are the observer and observer zenith, that's said, each point from the celestial sphere, when you are in the center of the celestial sphere, each point from you, from the center celestial sphere, this is 90 degrees of angular distance. Alright, so that's why when the body is rising, alright, the body's distance from the celestial sphere, alright, that's true altitude, because that's the angular distance by which the body has risen from the horizon. So this is the rational horizon, of course, this is the rational horizon, and when the body rises on the when you see a body rising, when it moves a distance from the horizon, this distance is called the true altitude. Alright, and that's why if I use a different pen here, 90 degrees minus true altitude gives you your zenith distance or true zenith distance. Alright, because each point on the rational horizon diagram is 90 degrees away from you when you are in the center of the globe here, and that's why 90 degrees minus the true altitude, that is how much the distance the body has risen from the horizon, gives you the zenith distance, true zenith distance, that you can see in the figure as well. Right, so I'll keep going and I'll come to the last drawing here, and there's nothing new to show you here. Basically, that again I'm trying to show you here is that again here, this is north latitude, because the equinoctial circle is south of you, so you as the observer are north of the equinoctial, and here the declination is also north. Declination is north, and by how I have drawn it, this is the declination, right? So by how I have drawn it, declination seems to be larger than the latitude, right? And that's it, that's pretty much it, that's all I have to tell you. So I hope that was easy for you. It's not too confusing, It's actually pretty simple and straightforward. If I was you and I was trying to understand this, I would start off with a meridian passage diagram that I showed you earlier, where I used to draw a vertical line and try to understand how the whole thing works. Basically, you have to understand that the system that you have in the Earth's sphere is projected onto the celestial sphere, and the concept of distances don't work. It's all angular distances, and otherwise bodies rising on the east and setting on the west, when it is exactly on your meridian, the meridian of Z, that is the meridian passage time. And rest of it is just follow what I've shown you here. You always stay in the center of the globe in the national horizon diagram, and the equinoctial moves with respect to you. So if you are north latitude, the equinoctial will go south of you. If you are south latitude, the equinoctial will go north of you. So the equinoctial circle moves, but you don't move on the national horizon diagram. Alright, I think I've pretty much covered the important bits and pieces. If you still think there's something you didn't understand and there's some clarification required, feel free to write to me in the comment section. And thank you for everybody who has subscribed, and if you have not subscribed and you've been watching my videos, please subscribe so you can get notifications about the new videos that I'm going to put up very soon. I'll see you soon with my next video. Bye.